most dangerous ideas are the ones that sound right but miss the point entirely. By 1945, after Trinity, after Hiroshima, the world knew my name. They knew about the bomb, about splitting atoms, about unleashing hell. What they didn't understand was the difference between destruction and creation, between breaking apart and building up. The press called everything atomic power, as if fission and fusion were the same beast wearing different masks. They weren't! They aren't! Nuclear fission tears heavy atoms apart. Nuclear fusion builds light atoms together. One destroys, one creates. The sun doesn't work like our bomb worked. The sun works by marriage, not divorce. By bringing things together, not ripping them apart. Every element heavier than hydrogen in your body was forged in a star's core through fusion, not fission. The misconception matters because it shapes how we think about the very process that makes life possible. Before we continue, take a moment to notice where you're listening from, and if this story stays with you, you're welcome to return tomorrow for what comes next. I first glimpsed the truth about stellar fire in Cambridge in the winter of 1925. I was 21. A graduate student wrestling with quantum mechanics under J. Thomson. When Arthur Eddington's work on stellar interiors crossed my desk, the paper was elegant, mathematical, precise. It proposed something that seemed impossible. The sun burned not through any chemical process we knew on Earth, but through the collision and marriage of atomic nuclei deep in its core. The numbers were staggering. Chemical combustion, the burning of coal or wood, releases perhaps 4 electron volts of energy per atom. Eddington calculated that nuclear processes could release millions of electron volts. The difference wasn't incremental. It was revolutionary. I remember sitting in the Cavendish laboratory, surrounded by the apparatus of classical physics, trying to comprehend what this meant. If the sun truly operated through nuclear fusion, if hydrogen atoms were somehow combining to form helium, then every assumption about energy and matter needed revision. Implications stretched beyond astronomy into the very fabric of reality. The problem that haunted astronomers was simple but profound. How could the sun shine? Lord Kelvin had calculated in the 1860s that if the sun burned chemically, it would exhaust itself in perhaps 30,000 years. Geological evidence suggested Earth was far older. The fossil record demanded millions, perhaps billions of years of steady sunlight. Something was wrong with our understanding. Eddington proposed the answer lay in Einstein's mass-energy equivalence. 4 hydrogen nuclei, if somehow fused into one helium nucleus, would create an atom slightly less massive than the sum of its parts. That tiny difference in mass, converted to energy, according to E=mc², could power the sun for billions of years. I spent months working through Eddington's calculations, checking his assumptions against quantum mechanical principles I was learning from Max Born in Göttingen. The mathematics held, more than held. They revealed something beautiful. The sun wasn't burning in any sense we understood burning. It was creating. Every second, 4 million tons of solar material converted to pure energy through the fusion of hydrogen into helium. This was my first encounter with a distinction that would later define my life's work. Fusion built things up. It took simple elements and forged them into more complex ones, releasing energy as a byproduct of creation. The process required immense temperatures and pressures, but once achieved, it could sustain itself for eons. In 1926, I moved to Göttingen to study under Born and James Franck. The quantum revolution was in full swing. Heisenberg was developing his uncertainty principle. Schrödinger was formulating his wave equation. I found myself at the center of a transformation in human understanding of nature's fundamental processes. It was there, in discussions with other young physicists, that I began to grasp the broader implications of stellar nucleosynthesis. If stars fused hydrogen into helium, what prevented them from fusing helium into heavier elements? The process seemed scalable, limited only by the balance between gravitational collapse and radiation pressure. Hans Bethe, whom I met during those European years, had already begun thinking about stellar evolution. He suggested that massive stars might forge elements as heavy as iron in their cores through successive fusion reactions. When such stars exhausted their nuclear fuel, they might collapse catastrophically, dispersing these newly created elements into space through supernova explosions. The picture emerging was one of cosmic creativity on an unimaginable scale. Stars were factories, forging the elements that would later form planets, oceans, and living beings. The carbon in our bodies, the oxygen we breathed, the iron in our blood, all had been created in stellar cores through fusion processes lasting millions of years. I returned to America in 1929 with this knowledge burning in my mind. The contrast between European sophistication in theoretical physics and American focus on practical applications was stark. Few American physicists seemed interested in stellar processes or cosmic nucleosynthesis. The country was entering the Depression, and abstract theoretical work felt indulgent. But I couldn't forget what I'd learned. At Berkeley, where I began teaching in 1929, I continued working on stellar collapse and nuclear processes. The calculations were complex, requiring new mathematical techniques and computational methods. We were trying to understand processes occurring at temperatures of tens of millions of degrees, pressures billions of times greater than Earth's atmosphere. The irony wasn't lost on me that I was studying creation while the world around me seemed intent on destruction. The economic collapse, the rise of fascism in Europe, the growing militarization of science, all pointed toward conflict. Yet here in my equations was evidence of nature's fundamental creativity. Processes that built complexity from simplicity, order from chaos. By the late 1930s, the pieces were falling into place. Bethe had worked out the detailed mechanisms of stellar fusion, the proton-proton chain and the carbon-nitrogen-oxygen cycle. We understood how stars could burn steadily for billions of years, how they created heavier elements, how their death throes enriched the universe with the materials necessary for planets and life. What we didn't yet understand was how to harness these processes ourselves. Fusion required conditions so extreme that they seemed beyond human capability to create or control. The temperatures needed were comparable to those in stellar cores. The pressures were enormous. Any attempt to recreate stellar fusion on Earth would require technologies we could barely imagine. Then came 1938 and Otto Hahn's discovery of nuclear fission. Suddenly, nuclear physics wasn't theoretical anymore. The splitting of uranium nuclei released energy in quantities that dwarfed chemical explosives. Within months, physicists around the world recognized the military implications. But fission was different from fusion. Where fusion created and built up, fission destroyed and broke down. Where fusion required enormous energy input to initiate, fission could proceed with relatively simple triggering mechanisms. Where fusion produced stable helium and heavier elements, fission produced radioactive fragments and lingering contamination. As Europe moved toward war in 1939, I found myself thinking about both processes. Fusion represented the cosmic creative principle, the force that made stars shine and life possible. Fission represented its opposite, the breaking apart of complex nuclei into smaller, often unstable fragments. Within a few years, I would be leading the effort to harness fission for weapons, but I never forgot the deeper truth I'd learned in those quiet Cambridge and Göttingen winters. Fusion was the universe's preferred method of energy production. It was clean, sustainable, creative, rather than destructive. If we could somehow master it, we might solve humanity's energy needs for millennia. The tragedy was that we learned to destroy atoms before we learned to marry them. The call came in September 1942. General Groves wanted to see me in Chicago. I knew what it meant. For 3 years, since Einstein's letter to Roosevelt, American physicists had been circling around the possibility of an atomic bomb. The theoretical work was complete. Fission could release unprecedented energy. The question now was engineering. I arrived at Los Alamos in March 1943, with fusion already occupying part of my mind. The immediate task was clear: build a fission weapon before the Germans did. The conversations with Edward Teller and Hans Bethe quickly turned to what we called the super. If we could trigger fusion reactions using a fission bomb as an ignition source, the explosive yield would be essentially unlimited. The irony wasn't subtle. Here we were, planning to harness the same process that powered the sun and created the elements of life, and we wanted to use it for the ultimate weapon of destruction. The contradiction troubled me, but not enough to abandon the work. The war demanded urgency. Hitler's scientists were pursuing their own atomic program. We couldn't afford moral luxury. Bethe understood the stellar physics better than anyone. He'd worked out the detailed mechanisms by which stars fused hydrogen into helium, the proton-proton chain reaction that had been burning in the sun for 4 billion years. In principle, we could recreate these conditions on Earth. The challenge was engineering temperatures of 10 million degrees and sustaining them long enough for fusion to occur. Teller was obsessed with the super from the beginning. While most of us focused on the immediate problem of plutonium and uranium fission bombs, he spent hours calculating fusion cross-sections and energy yields. His enthusiasm was infectious, but also disturbing. The man seemed to view fusion weapons not as a necessary evil, but as an intellectual challenge worthy of pursuit for its own sake. The technical discussions were fascinating despite their grim purpose. We knew that hydrogen nuclei, because of their positive electrical charge, repelled each other with enormous force. Only at stellar temperatures could they move fast enough to overcome this Coulomb barrier and fuse.
The process required what physicists called quantum tunneling, a phenomenon where particles could penetrate energy barriers that should classically be insurmountable. But achieving stellar temperatures on Earth presented problems that seemed almost insurmountable. Any material container would vaporize long before reaching fusion conditions.
The plasma would have to be confined by magnetic fields or inertial forces. Even then, the energy required to initiate fusion might exceed the energy released by the reaction itself.
Teller's early calculations suggested that a fission bomb might provide sufficient temperature and pressure to trigger deuterium fusion.
Deuterium, heavy hydrogen with an extra neutron in its nucleus, fused more readily than ordinary hydrogen. The reaction would produce tritium and helium, releasing roughly 4 times as much energy per unit mass as fission. The more we studied the super, the more complex it became.
Unlike fission, which could proceed in carefully calculated steps, fusion required achieving critical conditions almost instantaneously across a large volume of material.
The physics was well understood, but the engineering seemed to demand technologies we could barely conceive. I found myself in the strange position of directing a project to build fusion weapons while remaining fascinated by fusion as a creative cosmic process.
During evening walks around the Los Alamos Mesa, I often thought about the stars visible in that clear desert sky.
Each point of light represented a fusion reactor that had been operating steadily for millions or billions of years, converting hydrogen to helium and heavier elements with perfect efficiency. The contrast with our weapons' work was stark. We were trying to create uncontrolled fusion reactions lasting microseconds and designed to destroy cities. The stars achieved controlled fusion reactions lasting eons and designed to create the very elements that made life possible, the same fundamental process, but directed toward opposite ends. Beth shared my ambivalence. In our discussions, he often returned to the stellar applications of fusion physics. He was working out the details of how massive stars could fuse helium into carbon, carbon into oxygen, oxygen into silicon, and finally silicon into iron. Each step released energy while building complexity, creating the periodic table through successive generations of stellar evolution. These conversations reminded me why I'd fallen in love with theoretical physics in the first place. The universe revealed patterns of extraordinary beauty and elegance. The same quantum mechanical principles that governed fusion in stellar cores also determined the structure of atoms and molecules, the chemistry that made life possible, the forces that held matter together. But war had a way of reducing complex physics to practical questions. Could we build a deliverable fission weapon? How much plutonium would we need? What type of explosive assembly would achieve critical mass most efficiently? The super remained a secondary concern, intellectually interesting but technologically premature. By late 1943, we had detailed designs for both plutonium and uranium fission bombs. The physics was straightforward. Assemble enough fissile material quickly enough, and the chain reaction would proceed to completion in microseconds. The engineering challenges were immense, but solvable, with sufficient resources and talent. Fusion remained elusive. Teller's calculations showed that a fission bomb could probably initiate deuterium fusion in a properly designed device, but the uncertainties were enormous. We didn't know how efficiently the fusion fuel would burn, how much tritium we'd need, how to prevent the expansion of hot plasma from terminating the reaction prematurely. The moral weight of fusion weapons was different from fission. A fission bomb, however terrible, was limited by the amount of fissile material it contained. You could calculate maximum yields based on available uranium or plutonium, but fusion weapons had no theoretical upper limit. With enough fusion fuel, you could build bombs equivalent to millions of tons of conventional explosives. I began to understand that we were confronting choices that would define the post-war world. Fission weapons were horrible enough, but finite. Fusion weapons opened possibilities for destruction that exceeded anything in human history. The same process that made stars shine and life possible could, in human hands, become an instrument of species suicide. Yet we continued the work. The war demanded it. The fear of German atomic weapons drove us forward. And beneath the immediate urgency lay a deeper scientific compulsion. We were exploring fundamental forces of nature, pushing the boundaries of human knowledge into realms previously reserved for stellar interiors. The tragedy was becoming clear even then. We would master atomic destruction before atomic creation. We would learn to make fusion bombs before fusion power plants. The same knowledge that could solve humanity's energy needs for millennia would first be applied to building the ultimate weapons of war. The headline screamed "Atom Bomb" in letters 3 inches tall, August 6th, 1945. Hiroshima had been destroyed by a single weapon, and suddenly every newspaper in America wanted to explain nuclear physics to readers who had never heard of uranium or chain reactions. I watched the coverage with growing dismay. The press reduced everything to splitting the atom, as if that phrase captured the full complexity of nuclear processes. Life magazine published diagrams showing atoms breaking apart in cartoon explosions. Time called it atom smashing. Newsweek explained that scientists had learned to tear atoms apart. The language mattered because it shaped understanding. When every nuclear reaction became splitting atoms, the public lost the crucial distinction between breaking things down and building things up. They couldn't grasp that the sun worked through an entirely different process than the bombs we dropped on Japan. I tried to clarify in interviews. In late August, I spoke to William Lawrence of the New York Times. I explained that nuclear fission involved heavy elements like uranium breaking into smaller pieces, while nuclear fusion involved light elements like hydrogen combining into heavier ones. I emphasized that the sun powered itself through fusion, not fission. Lawrence listened politely, took notes, then published an article titled "Scientist Explains Atom Splitting." The subtitle read, "Process, same as in sun." Oppenheimer says, "He had turned my careful explanation of two different processes into a claim that bombs and stars worked identically. The misunderstanding wasn't entirely the reporter's fault. Nuclear physics defied common sense. People understood that things could be broken apart, split, shattered. The idea that tiny particles could be forced together to release energy seemed counterintuitive. Breaking things released energy in everyday experience. Building things required energy input. But nuclear physics operated by different rules. At the scale of atomic nuclei, the relationship between mass and energy became paramount. When heavy nuclei like uranium split apart, the fragments had slightly less total mass than the original nucleus. The missing mass converted to energy according to Einstein's equation. When light nuclei like hydrogen fused together, the product again had less mass than the ingredients. Both processes released energy, but through opposite mechanisms. I gave talks at universities, trying to educate audiences who might influence public opinion. At Harvard in September 1945, I drew diagrams on a blackboard showing the binding energy curve that governed nuclear reactions. Elements lighter than iron released energy when fused together. Elements heavier than iron released energy when split apart. Iron sat at the peak, the most stable nucleus in nature. The audience included physics professors and graduate students who understood the mathematics. They grasped why stellar fusion could operate for billions of years, building elements up the periodic table until stellar cores were filled with iron. They understood why uranium fission could power weapons but not stars. But these academic audiences represented perhaps 0.1% of the American public. Everyone else got their nuclear education from newspapers and magazines that preferred simple explanations to accurate ones. Atomic power became the universal term for any nuclear process, whether destructive or creative. The confusion deepened when President Truman announced our hydrogen bomb program in January 1950. The press immediately called it a superatom bomb, missing entirely that hydrogen weapons worked through fusion rather than fission. Headlines proclaimed, "Scientists build bigger atom smasher," when the truth was nearly opposite. We were learning to force atoms together, not smash them apart. I found myself in the peculiar position of being famous for weapons I'd helped create while being unable to communicate the fundamental physics that made them possible. The public knew my name associated with destruction, with splitting atoms, with unleashing forces that could end civilization. They had no idea I'd spent years studying the creative processes that made life possible. The irony cut deep. Every carbon atom in their bodies had been forged in stellar cores through fusion reactions. Every oxygen molecule they breathed represented the death of a massive star that had fused silicon into iron, then exploded to scatter its nuclear products across space. The calcium in their bones, the iron in their blood, the gold in their wedding rings, all testified to the creative power of stellar nucleosynthesis. But none of this penetrated public consciousness. Nuclear meant dangerous. Atomic meant destructive. The same prefix that described the fundamental creative process of the universe had become synonymous with annihilation. I began to understand how scientific literacy shaped political possibilities. A public that couldn't distinguish fusion from fission couldn't make informed decisions about nuclear policy. They couldn't evaluate the promise of fusion power or the risks of fusion weapons. They couldn't appreciate the cosmic context that made Earth's existence dependent on stellar fusion reactions. The confusion had practical consequences. When scientists proposed fusion power research in the early 1950s, public reaction was largely negative.
People heard nuclear power and thought of bombs, not the clean energy source that had powered the sun for 4 billion years.
Opposition to nuclear research conflated weapons development with peaceful applications, making rational energy policy nearly impossible.
I watched congressional hearings where senators questioned fusion researchers about radiation hazards that didn't exist in controlled fusion reactions. The politicians couldn't grasp that fusion produced helium, one of the most inert substances in nature, while fission produced dozens of radioactive isotopes with half-lives ranging from seconds to millennia.
The educational failure extended beyond nuclear physics. The public lost any sense of humanity's cosmic context. They couldn't see themselves as products of stellar evolution, composed of elements forged in nuclear furnaces billions of years before Earth existed. They couldn't appreciate that every sunrise represented the continuation of fusion reactions that had sustained life for geological ages. Science became something alien, dangerous, incomprehensible. Scientists became either saviors or destroyers, rather than people trying to understand natural processes that had operated long before humans existed and would continue long after we were gone. I shared responsibility for this confusion. My association with weapons development overshadowed any attempts to explain the underlying science.
When I spoke about fusion as a cosmic creative process, audiences heard the man who had built atomic bombs talking about more efficient ways to destroy cities.
The tragedy wasn't just educational. It was moral and political. A society that couldn't distinguish creation from destruction at the nuclear level would struggle to make wise choices about technology, energy, and the relationship between scientific knowledge and human welfare. By 1950, 5 years after Hiroshima, the misconception had crystallized into accepted wisdom. Nuclear physics meant weapons. Atomic energy meant destruction. Fusion and fission were technical variations on the same theme of splitting atoms and releasing dangerous forces. The truth remained what it had always been. Fusion built up while fission broke down. The sun married hydrogen nuclei while bombs divorced uranium atoms. Creation and destruction operated through opposite nuclear mechanisms, but the public couldn't see the difference. This blindness would shape nuclear policy for decades to come. To understand fusion properly, you must first grasp the extraordinary conditions inside a star. The sun's core reaches 15 million degrees Celsius. The pressure exceeds 200 billion Earth atmospheres. Under these conditions, matter exists in a state unknown on our planet's surface. A plasma, where electrons have been stripped from atomic nuclei, and particles move at velocities approaching 10% the speed of light.
These numbers represent more than academic curiosities. They define the threshold where nuclear fusion becomes possible, where the fundamental creative process of the universe can operate.
At lower temperatures, atomic nuclei cannot overcome their electrical repulsion. At lower pressures, they cannot approach closely enough for the strong nuclear force to bind them together. I spent years working through the detailed mathematics of stellar nucleosynthesis, first with Bethe during our Los Alamos collaboration, later with graduate students at Berkeley. The calculations revealed a universe far more sophisticated than anything we had imagined. Stars were not simply burning gas balls, but precisely regulated nuclear reactors operating through feedback mechanisms of extraordinary elegance. The basic fusion process in stars like our sun follows what we call the proton-proton chain.
Two hydrogen nuclei, moving at enormous velocities, approach each other closely enough that quantum mechanical tunneling allows them to overcome their electrical repulsion.
When they fuse, one proton converts to a neutron through beta plus decay,
Creating a deuterium nucleus, a positron, and a neutrino.
The deuterium nucleus then fuses with another proton to form helium-3, releasing a gamma-ray photon. Two helium-3 nuclei can then combine to produce helium-4, liberating two protons that can participate in additional reactions. The net result converts 4 hydrogen nuclei into one helium nucleus, with the mass difference appearing as energy according to Einstein's equation. The process seems straightforward when described in words, but the reality involves quantum mechanical phenomena that challenge intuition. The probability of any individual proton-proton collision resulting in fusion is extraordinarily small, roughly 1 chance in 10 billion billion. Yet the sun's core contains so many protons moving at such high velocities that 4 million tons of hydrogen convert to helium every second. This conversion releases energy equivalent to 90 billion 1 megaton hydrogen bombs every second, sustained continuously for 4.5 billion years. The energy production density in the sun's core actually exceeds that of a compost pile by only a factor of a few hundred, but the sun's enormous volume makes the total output capable of powering our entire solar system.
The energy produced in stellar cores faces a journey that can last hundreds of thousands of years before reaching the surface. Gamma-ray photons generated by fusion reactions collide repeatedly with electrons and nuclei, losing energy and shifting toward longer wavelengths with each interaction. By the time this energy emerges from the sun's photosphere, it has been transformed into the visible light and infrared radiation that warm our planet. But hydrogen to helium fusion represents only the beginning of stellar nucleosynthesis. In massive stars, 8 times heavier than our sun or more, core temperatures eventually reach 100 million degrees.
At these temperatures, helium nuclei can overcome their greater electrical repulsion and fuse together through the triple alpha process, creating carbon 1,2.
This reaction fascinated me because of its apparent improbability. 3 helium, 4 nuclei must collide simultaneously, or nearly so, because the intermediate beryllium-8 nucleus is unstable and decays in about 10 to the minus 16th seconds. For years, astronomers couldn't understand how stars produce significant amounts of carbon through such an unlikely process. The solution came from Fred Hoyle's insight about resonance states in carbon 1,2. If the carbon nucleus possessed an energy level exactly matching the combined energy of 3 helium-4 nuclei, the reaction rate would increase dramatically. Hoyle calculated the required energy and predicted that such a resonance must exist. When experimenters looked, they found it precisely where Hoyle had predicted. The discovery revealed something profound about the relationship between nuclear physics and cosmic evolution. The existence of carbon, and therefore the possibility of carbon-based life, depended on an extraordinarily precise match between nuclear energy levels and stellar conditions. A small change in the strong nuclear force would have made carbon production impossible. Once massive stars begin producing carbon, the nuclear burning continues up the periodic table. Carbon nuclei can fuse with helium to produce oxygen. Oxygen can capture helium nuclei to become neon. Silicon burning produces elements up to iron 5,6, the most stable nucleus in nature. Each stage requires higher temperatures and operates on shorter timescales. Hydrogen burning can continue for millions of years. Helium burning lasts perhaps 1,000,000 years. Carbon burning proceeds for centuries. Silicon burning consumes its fuel in days. The star rushes toward a nuclear dead end where no further energy-producing reactions are possible. Iron 5,6 sits at the peak of the nuclear binding energy curve. Fusion reactions that produce nuclei lighter than iron 5,6 release energy. Fission reactions that break apart nuclei heavier than iron 5,6 also release energy. But iron itself cannot participate in energy-producing nuclear reactions. When a massive star's core fills with iron, nuclear burning stops abruptly. Without energy production to balance gravitational collapse, the star's core contracts violently. In less than a second, a core the size of Earth shrinks to a sphere perhaps 20 kilometers in diameter. The gravitational potential energy released in this collapse heats the outer layers to billions of degrees and blasts them into space in what we observe as a supernova explosion. These stellar death throes scatter the products of nucleosynthesis across space. The carbon, oxygen, silicon, and iron forged in stellar cores during millions of years of nuclear burning return to the interstellar medium, where they can eventually incorporate into new stars, planets, and living beings. Every element in your body heavier than hydrogen was created in this way. The calcium in your bones was synthesized in a massive star's core through successive helium capture reactions. The iron in your blood was produced during silicon burning in the final days before a supernova explosion. The gold in any jewelry you wear was created during the supernova explosion itself, through rapid neutron capture processes impossible under normal stellar conditions. This cosmic perspective transforms our understanding of nuclear fusion. The process represents not merely a source of energy, but the fundamental creative mechanism of the universe. Fusion builds complexity from simplicity, forging the 92 naturally occurring elements from primordial hydrogen and helium produced during the Big Bang. The elegance of stellar nucleosynthesis rivals anything in human art or literature. Through precise regulation of temperature and pressure, stars produce exactly the elements needed for rocky planets and biological evolution. The reaction rates proceed at exactly the pace required to sustain energy production for billions of years, providing stable conditions for planetary evolution. Yet humans learn to harness fusion only for destruction. Our hydrogen bombs recreate stellar core conditions for microseconds, releasing in an instant the energy that stars produce steadily over millennia. We mastered the physics of creation in service of annihilation, missing entirely the deeper lesson about fusion as the universe's preferred method of building order from chaos. The irony cuts deeper when you consider that controlled fusion power could solve humanity's energy needs for geological ages.
The fusion reactions that power stars could power human civilization without producing long-lived radioactive waste or greenhouse gases. The fuel exists in virtually unlimited quantities in seawater. The process is inherently safe, shutting down automatically if conditions deviate from precise requirements.
But achieving controlled fusion requires recreating stellar conditions in Earth-bound machines containing plasmas at hundreds of millions of degrees for seconds or minutes rather than microseconds.
The engineering challenges dwarf anything we accomplished during the Manhattan Project. The sun achieves fusion through gravitational confinement, using its enormous mass to create the pressure and temperature needed for nuclear reaction. We must substitute magnetic fields or inertial forces, technologies that barely existed when I first understood the stellar fusion processes in 1920s Cambridge. The real tragedy isn't that we built fusion weapons before fusion power plants. It's that we learned to destroy stars before we learned to build them. In the spring of 1967, I delivered the Wooden Lectures at McMaster University in Ontario.
The topic was The Flying Trapeze, 3 Crises for Physicists. I chose the title deliberately.
Physics had become a performance art, scientists swinging between discoveries and their consequences with no safety net, no guarantee of landing safely. By then, 22 years had passed since Trinity. 27 years since I'd first grasped the distinction between fusion and fission that the public still couldn't see. I was 63 years old, my security clearance long revoked, my role in weapons development a matter of historical record. Time enough for reflection, for honesty about what we had accomplished and what we had failed to achieve. The misconception about nuclear fusion persisted with depressing consistency.
Popular magazines still described hydrogen bombs as superatom splitters. Science textbooks conflated nuclear reactions under the general heading of atomic energy. Even university physics students
struggled to explain why the sun didn't work like a fission reactor. The failure went deeper than scientific literacy. It represented a breakdown in the relationship between knowledge and wisdom, between technical capability and moral understanding. We had mastered the physics of stellar cores while remaining blind to their cosmic significance. We had learned to recreate the conditions that forge elements while missing the creative principle that makes life possible. I had played a central role in this tragedy. My association with weapons development overshadowed any attempts to communicate the beauty of nuclear physics as a creative force. When I spoke about fusion as cosmic creativity, audiences heard the father of the atomic bomb talking about more efficient methods of destruction. The irony poisoned every attempt at public education. But the responsibility extended beyond my personal history. The entire scientific community had failed to convey the fundamental distinction between building up and breaking down, between the processes that create complexity and those that destroy it. We had allowed the public to believe that all nuclear reactions were variants of atomic destruction, missing entirely the role of fusion in making life possible. The consequences shaped policy in ways we were only beginning to understand. Public fear of nuclear processes made controlled fusion research politically difficult. Funding agencies hesitated to support projects that seemed connected, however distantly, to weapons development. The same knowledge that could solve humanity's energy needs for millennia became suspect because of its association with bombs. I watched younger physicists struggle with this legacy. Brilliant researchers who could have advanced controlled fusion instead found themselves defending basic science against public suspicion. The gap between scientific understanding and public knowledge widened with each passing year, making rational energy policy increasingly impossible. The tragedy was unnecessary. Fusion and fission operated through opposite mechanisms, produced different products, posed different risks and benefits. Fusion broke heavy nuclei apart, producing radioactive fragments that remained dangerous for thousands of years. Fusion combined light nuclei together, producing stable helium that posed no environmental threat. The distinction mattered for practical reasons, but also for something deeper. How we understood nuclear processes shaped how we thought about nature, technology, and human purpose. A society that couldn't distinguish creation from destruction at the fundamental level would struggle to make wise choices about any advanced technology. The sun had been demonstrating controlled fusion for 4.5 billion years. Every sunrise testified to the possibility of clean, abundant energy through nuclear processes that produced no long-lived waste, no greenhouse gases, no environmental contamination. Yet humans remained fixated on the destructive applications we had mastered first. During my McMaster lectures, I tried once more to explain the cosmic context that made Earth's existence dependent on stellar nucleosynthesis.
Every element in our bodies except hydrogen had been forged in stellar cores through fusion reactions lasting millions of years. The carbon that formed the backbone of organic molecules, the oxygen that enabled cellular respiration, the iron that carried oxygen in our blood, all represented the creative output of stellar fusion processes.
The audience listened politely, asked thoughtful questions, applauded at appropriate moments. But I could see in their faces the same confusion I had encountered for 20 years.
Nuclear physics remained abstract, dangerous, incomprehensible. They couldn't connect the equations I wrote on blackboards to the sunrise they would see the next morning.
The failure wasn't theirs. It was ours. We had developed the most powerful technology in human history without developing adequate language to explain it.
We had split atoms before we could split the difference between creation and destruction in public consciousness.
I thought often about the young physicist I had been in 1925, reading Eddington's papers about stellar energy production in the Cambridge Library. That young man had grasped immediately that fusion represented cosmic creativity, the fundamental process that built complexity from simplicity. He had seen the beauty in stellar nucleosynthesis, the elegance of hydrogen marriage producing helium offspring while releasing energy that could sustain life for billions of years.
What had we lost in the translation from theoretical understanding to practical application? At what point did the creative principle become subordinated to destructive capability? When did the process that makes stars shine become primarily a method for building bigger bombs?
The answers mattered because they would shape humanity's relationship with nuclear technology for generations to come.
If we could recover the sense of fusion as cosmic creativity, we might yet develop the controlled fusion power that could liberate our species from dependence on fossil fuels. If we remain trapped in the misconception that all nuclear processes were variants of atomic destruction, we would miss the opportunity to harness stellar energy for human benefit. The choice wasn't primarily technical. The physics of controlled fusion was well understood.
Magnetic confinement, inertial confinement, the various approaches to containing fusion plasmas long enough for net energy production, all represented engineering challenges rather than fundamental obstacles. The barriers were psychological, political, cultural. We needed a new language for nuclear physics, one that emphasized creation over destruction, building up over breaking down. We needed educational approaches that connected nuclear processes to their cosmic context. Most importantly, we needed scientists willing to engage seriously with public misunderstanding rather than dismissing it as ignorance.
The responsibility was mine as much as anyone's. I had helped create the association between nuclear physics and weapons. I had participated in reducing stellar creativity to destructive application.
The knowledge that could have been humanity's greatest gift became its greatest threat because we had approached it backwards, learning to destroy before learning to create.
But understanding the problem suggested the solution. If we could communicate the true nature of fusion as a cosmic creative process, we might yet inspire the political will necessary for controlled fusion development.
If we could help people see themselves as products of stellar nucleosynthesis, composed of elements forged in nuclear furnaces billions of years before Earth existed, we might change their relationship with nuclear technology entirely.
The sun would rise tomorrow morning, as it had every morning for 4.5 billion years, powered by the same fusion reactions that could solve humanity's energy needs forever. Whether we learned to harness that cosmic creativity or remained trapped in our destructive misconceptions would depend on choices we had yet to make. I had spent my career studying the forces that make stars shine and elements possible. The physics was beautiful, elegant, profound. The applications could be transcendent or catastrophic. The difference lay not in the nuclear processes themselves, but in human wisdom about how to use them.
That wisdom remained to be developed. The choice between cosmic creativity and terrestrial destruction remained to be made. The misconception about nuclear fusion remained to be corrected.
The future depended on getting it right.